Good afternoon, everyone. This is Shimeng Yu from Georgia Tech. Due to the travel restrictions caused by the coronavirus outbreak, I couldn't join the date conference, unfortunately. So here we are going to share our research progress in this topic through this video presentation. So the title of this talk is Overcoming Challenges for Achieving High in situ training accuracy with Emerging Memories. And the leading author of this paper is Zhanshi Huang, and this work is supported in part by NSF and also the SRC grants. So this is the outline of the presentation. First, I will give the motivation, challenges, and the algorithm structures we used. And then we will discuss the effects of each non-ideal device effects and propose the possible mitigation methods. So here are the problems we want to tackle include the nonlinearity asymmetry in the weight update of the synaptic devices, and also the device-to-device cycle-to-cycle variations, and also the number of states of the devices. So those are the potential non-ideal effects from the device perspective. And then we will talk about, first, let's start with the motivation. So as everyone is aware, today the hardware accelerators for machine learning is becoming more and more important. So if you look at the hardware platforms for machine learning, of course, GPU still is the mainstream technology for training, especially at the data center or the cloud side. But we see that the ASIC solution of the accelerators, for example, the Google's TPU, is becoming more and more popular. So in the ASIC solutions, typically there will be multiple PEs made of the MAC arrays, and then the data is stored in the shared SRAM on chip, and then we have the pooling activation and those special units as well. Because on-chip memory here, the shared SRAM is limited, so still we need to have the frequent access to the DRAM for the parameters during the training or even in the inference. So this kind of architectures still are limited by the memory wall problem. So that is the data access between the processing units and the memory units. To overcome this kind of memory wall problem, the research community has been advocating the computing memory paradigm, where the weights of the neural network are stored in the memory array, whereas activations are loaded as inputs to the word length of the memory array to do the computation within the memory array. And this can enable the parallel access to multiple word lengths, and then we can do the summation of the currents along the bit length. So we can eliminate the digital MAC units in this design, and then we use the analog to digital converters, the ADCs, as the edge of the array to convert the data back from the analog domain to the digital domain. So in this approach, we can reduce the data movement, especially the weight movement, because we only load in the input and then buffer out the output. With this kind of approach, there are many progresses in the past few years. At least in my group, we have been working on the SRAM-based computing memory approach. And here is an example of the paper we presented in DAC 2018. And this is prototype chip we tape out with collaborations from the National Tsinghua University, Taiwan. And also here recently we collaborate with our colleagues at Arizona State University and taped out the ARM-based computing memory prototype. So in this case, we use the resistive memory as a weight element and enable the parallel computations within this 128 by 64 ARM array. So here we have the peripheral circuits like the analog mux and ADCs integrated on chip, and the ARM is monolithically integrated on top of the CMOS platform. So this is our recent demonstrations published in this IEEE Macro paper. So although there are many progresses so far, still the challenge today is with the training, and because inference is easier, and most of the recent demonstrations are targeting at the inference problem, but the training is much more difficult. Before we talk about that, we can first look at what kind of computing memory architectures are proposed in the field. So here, the first one is SRAM-based design, where we can have multiple SRAM or cells grouped as one synaptic weight. This is because SRAM is 1 bit per cell, so we have to use multiple SRAMs to represent multi-bit weight. But we can enable multiple word lengths even in the SRAM-based design, and then we can do the summation of the current along the bit line, and then quantize the partial sum through the ADC as a preferred circuits. And then we need to use adder and shift register to accumulate the partial sums. This is because we have different significance among different columns of the SRAM array. And similar approach can be applied to the non-volatile memory-based design. And for non-volatile memory, we can have two-terminal devices or three-terminal devices. For two-terminal devices, typically we can use the 1T1R structure. This R can be, for example, R1, resistive random access memory or phase change memory. And then for the three-terminal design, here we may have the three-terminal synapses like the ferroelectric transistor or even the floating gate flash transistor. So no matter what, we will sum up the current along the column and then again do the quantization of the partial sum through the ADC and then shift and add to accumulate the partial sum. So the non-ideal effects in the emerging memory-based computing memory accelerator included the following. So those are the key challenges, especially for the training. And here, first we can look at the device level non-ideal effects. So in the device level, we may have the nonlinearity and asymmetry of the weight updates. That means the conductance tuning is a nonlinear and asymmetric function as the number of pulses. So as shown here in this figure. And also we may have the C2C, that is cycle-to-cycle variation. That means here when we update the conductance with the pulses, then there will be some variations in the conductance after each programming pulse. And also we may have device-to-device variation, that is the weight update baseline may have some variations among different devices. And lastly, we may have this limited number of states. This depends on the device's property, how many levels we can achieve with the programming pulses. So the circuit level non-ideal effects mostly is due to the ADC quantization loss. So this is when we sum up the current along the column, we need to use the ADC to quantize the partial sum. So here, this is the distribution of the partial sum. And then after the ADC quantization, we are going to basically quantize that into the discrete levels. And the challenge here is that the ADC is expensive in terms of the area and also the energy consumption. So the low precision ADC is needed from the overhead point of view. However, this may introduce the quantization loss for the algorithm, because here the partial sum may not be accurate if the ADC resolution is too low. So those are non-ideal effects that may affect the training performance of the accelerator based on the emerging non-volatile memories and using this computing memory approach. So in this work, we're trying to identify the key challenges and then propose the possible mitigation strategies to improve the training performance. And here we use an algorithm baseline based on this modified weak structure. So what is weak? Weak is an algorithm proposed by those authors in this paper. So WAGE stands for the quantization of the weight, activation, gradient, and error. So basically all the computation steps during the training are quantized in this weak algorithm. And here, for example, we can say this kind of diagram to show the process of the training. First, we load in the activation from the previous layer, and then the activation will do the convolution with the weights. And here we consider the partial sum. And so we are going to use ADC to do the quantization. And then after that, we're going to go through the activation function. And then after activation function, we're going to do quantization again. So this is forward process. And in the backward process, we are going to basically compare the prediction of the last layer with the labels and get the error. And with this error as input, then we're going to load in the error, the quantized version of the error as the input to convolve with the weight transpose. And then the weight, the convolution results will be the error to the next layer. So here this is transposed weight and then convolve with the error, and then the output will be the error to the previous layer. So this is second step, the backward propagation. And after that, then we may need to do the gradient calculation using the error here we obtained, and then the activation in the feed-forward process. So those two needs to do the MAC operation again to get the gradient of the weights. And then after a batch, we're going to accumulate this kind of gradients of weights and finally do the weight update, that is to apply the delta W to the weight. So here we are going to consider most of the non-ideal device effects to the gradient calculation and weight update process. For example, those non-ideal effects like nonlinearity and asymmetry and device-to-device variation, cycle-to-cycle variation. So those apply to this non-ideal weight update process. And also in this work, we are going to introduce some momentum concepts to the gradient calculation step. We will talk about that later. So this is additional step we add to the algorithm. So let's discuss the effects of each non-ideal device effects and propose the possible mitigation methods. So first one is the weight update nonlinearity and asymmetry. So here again we show the normalized conductance of the devices as a function of the programming pulses. So here we have these labels from 0 to like a positive line and a negative line. So this represents the nonlinearity. And asymmetry is going to use the sign, like positive sign for the weight update, like this, and then negative sign to represent the weight decrease, like this. So then this is the asymmetry. If we increase with a positive sign and then decrease with a negative sign here. So this has been a known issue in the device research community, and I think prior work, including our own work at IBM's analysis, suggested that the asymmetry is a killing factor of the training accuracy. So here we show that the training accuracy for the CIFAR10 dataset as a function of the nonlinearity level. So here this black curve is with asymmetry because the increase of the weight is positive and then the decrease of the weight is negative. So here you can see that the training accuracy quickly drops with increasing the nonlinearity combined with asymmetry. However, if the increase and decrease of the weight follow the same kind of trajectory, That means we increase with positive sign here and decrease with the same positive sign here. Then that means here the red curve is positive and positive. If we have this kind of nonlinearity, even up to 6 or even up to 8, so then the accuracy does not degrade too much if the update is symmetric. So here we identify the key challenge is the asymmetry instead of the nonlinearity. So what really contribute to this accuracy loss is due to the conductance distribution eventually we get. This is understandable by this diagram here. For example, if we keep increasing the weight by those 3 steps, and then the next cycle, if the weight update requires a negative, let's say the decrease of the weight, if we use this kind of weight update curve, we are going to jump from this blue curve to the red curve and then apply a negative pulse. So the device will drop significantly in the conductance. So in other words, it's very easy for the device to jump from those high conductance region back to the middle of the conductance region. In other words, because of this asymmetry, the device tends to go back to the middle of the conductance distribution. This is evidenced by the plots. We show the statistics of the training results. First one, this one is without this kind of nonlinearity. This is perfect linear updates, like the software. After the training at epoch 185, that's towards the end of the training, you can see the distribution of the weight, that means the conductance of the devices, is quite uniform. That means all the conductance states are possible in the final convergency states. However, with this kind of positive 3 minus 3 asymmetry, you can see that most of the conductance actually is centered in the distribution. This is because this kind of jumping back effect is easier for the conductance to jump back to the middle of conductance states, because here there is abrupt change if we have the sign change from positive to the negative. So this is a key problem we identified. And if you think about the sign change during the weight update process, that's possible delta W sign change scenario. First one is sampling error in the batches. So this is normal during the training process, like the green ones. Second one is the oscillation around the local minima. So we have the sign change like this. So it will oscillate around the local minima. And then the third one is the oscillation around the global minima. So this is what we eventually want to get. So what we'll try to propose here is to add the momentum during this weight update process to keep the trajectory for the decreasing trend of the loss function in this energy landscape. So here what we propose is to add a momentum factor beta. So this essentially will remember a fraction of the weight update in the previous step, and then plus 1 minus beta, another fraction of the current gradient calculation results. So that means we can remember the momentum of the training. So if the momentum is keep increasing, then at this current step, even the gradient calculation tells you to go back, but because of the momentum, we may still want to go up. So this can avoid this kind of unnecessary sign change during the weight updates. This can avoid the jumping back effect to the center of the conductance distribution due to the asymmetry in the weight updates. And also we consider the device-to-device variations, cycle-to-cycle variations, and then the number of the states is limited by the device properties. So here we consider different kind of devices. They range different precisions from like 5 bits to even 10 bits. And then the cycle-to-cycle variation typically is like 1 to like 3%. And then here is the nonlinearity factor with the symmetry, some of them. So those are the typical data from the reported devices in the literature. And a few more words on the ADC quantization effect, because ADC is going to compare the partial sum with the fixed reference by the, for example, comparator. So then it will have a fixed trend to round the partial sum down. So that means we are going to bias the quantization results towards the negative side. So this is bad for ReLU kind of activation because the ReLU will assume 0 if the partial sum is smaller than 0. So here we try to add positive 1 to the least significant bit of the negative partial sum. So effectively, we are going to round up instead of round down of the negative partial sum. But for the positive partial sum, we still round it down. So with this kind of technique, we can compensate some of the ADC quantization loss. All right, let's go over the simulation results. So here is the settings for the study. So we use a PyTorch platform, and then we work on this 8-layer VGG network for CIFAR10 dataset. Because we use this WAG framework, so we quantize everything during the training process. That means the weight is quantized to be 8 bits, gradient is 8 bits, and then also 8-bit activation and 8-bit error. So this is hardware friendly. And the baseline accuracy from the software training is 92% of this network. And here we assume 128 by 128 subarray size for the partial sum quantization. First, we look at the effect of the momentum. So here we try different momentum factor, the beta value, and then here is to study the case where the potentiation and depression is like positive 3 and negative 3, those nonlinearity factors. So we can see that with point line beta factor, it can achieve like above 90% of the accuracy. So with this kind of point line beta factor, we run the different nonlinearity levels with the symmetry. So you can see that if we further tune the learning rate, this black curve, so we can achieve fairly stable training accuracy, even the nonlinearity is very large, like even nonlinearity is like 8 or 9, so still we can achieve like 89% accuracy. So this is much improved than the previous results reported in the literature. Also from the distribution of the conductance states after the training, then you can see that with the momentum vector quantum line, the blue distribution will tend to spread out instead of concentrating to the middle of the conductance. That means this momentum can help stabilize the distribution to a wider or more uniform distribution. And also we checked a few other parameters during the training, for example, the batch size. So the red curve is the training performance as a function of the epoch number. As you can see here, this is without momentum, and the accuracy eventually reach like 80%. But if we increase the size batch size to be like from 200 to 4,000, then we can further increase the training accuracy a little bit. However, if we want to really approach the software baseline, for example, like 90%, we do need to add the momentum, that beta factor, 0.9. And then even with the device-to-device variation, so the blue curve is with the device-to-device variation. And then we can still achieve like 90% accuracy. So we can argue that device-to-device variation is not a big problem. One more thing is the momentum factor. So here we need to also quantize the momentum and to save the memory storage in the hardware. So here we quantize the momentum of the gradients from like 16 bits to 6 bits. As you can see, we still want to maintain the momentum. It's like around 10 or even 12 bits. So in our design, the momentum will be most demanding for the precision, other than the like weight or gradients. They just need 8 bits, but momentum for us may be like 10 to 12 bits. And then we consider the limited number of states of the device. So here you can see that with the decrease of the device precision from 8 bit to 4 bit, then the accuracy will drop quickly. But if we fine tune the learning rate, then we can still achieve reasonably good accuracy, even the device precision is like 4 bits. Here is the cycle-to-cycle variation, and the conclusion here is that the cycle-to-cycle variation will first decrease the accuracy, but this degradation depends on the nonlinearity factor and also the precision of the device. So if, for example, here the precision of the device is high and the nonlinearity factor is low, for example, the black curve here, so we can achieve initial very high accuracy, but the accuracy quickly drop. This is because when we have this small nonlinearity, and then we have the large cycle-to-cycle variation, as you can see here in this statistical program, diagram. So you can see many of the weight updates will have either sign positive or sign negative. So that means a sign change in the weight updates. So we want to avoid this kind of sign change because that will create the problem of the jumping back of the conductance to the middle of the distribution. So this is very undesired. And on the other case, if the nonlinearity is low and the weight precision is also low, so of course we will start with the very, let's say, not good accuracy, but it's fairly stable over the cycle-to-cycle variation. This is also can be understood by this kind of diagram. Due to the time limitation, I will skip the detailed discussions here. Okay, the ADC quantization problem. So here we consider 128 by 128 subarray size, and for the training, we see that we need at least 7-bit or 8-bit ADC to approach the software baseline. So here, this is very high demanding in terms of the ADC precision. For inference of the same network, we can actually only use like 3-bit or 4-bit ADC to maintain the same accuracy. But for training, we need like 8-bit at least. So here, combining all the non-ideal effects, this is the final training performance. Assuming like a nonlinearity or symmetry is positive 3, negative 3, ADC precision is 8 bits, and then device-to-device variation is like this 0.5, and cycle-to-cycle variation is 3%, momentum is 12 bits, and number of device states is 6 bits. So here, this is the training performance. Eventually, we can get 86% of the accuracy, which is reasonably good considering we combine all those non-ideal effects. Okay, so here is the conclusion of this work. So in this work, we overcome the grand challenges for in situ training with emerging non-volatile memories. First, the asymmetry and nonlinearity is no longer a problem if the momentum is introduced in the weight updates. Device-to-device variation is not a concern either. That means the low precision training is also possible. However, the sec-to-sec variation needs to be paid attention. This is more problematic. Device engineering is needed to further suppress the cycle variation. And ADC resolution requirement is still very high for the on-chip training. 8 bits means a lot of overhead for the hardware peripheral circuits. So we believe that this work could potentially pave a theoretical milestone for achieving high in situ training accuracy with those analog emergent non-volatile memory-based synapses. So that's the end of the presentation, and thank you so much for your attention to this work. If you have questions, feel free to send us an email with your questions. We're happy to answer that. Thank you.